All right, folks, we are back. We are live. Thank you so much for your patience. Sometimes, we just have some tech issues. It's just one of
That
those
works.
days. But
Zoom
we've
world.
got it all sorted out. And if you're just joining us, once again, we are joined by York University's Jesse Rogerson, who studies quasars. Really amazing things out there in the universe related to black holes, one of my favorite topics. He'd already been talking about them for about 5 minutes, which I was really engrossed by. Thank you so much for your patience, Jesse.
No worries.
So for all you watching, we're going to talk about quasars, and we are going to talk a little bit about the new telescope that NASA is setting up in a space that Canada is going to be involved in. So for the next 30 minutes, we'll go a bit later than our normal time because we had some tech issues as we're going to wait for some people to get in here. But Jesse, thanks so much. Let's get into quasars and get back to that presentation.
Okay, so should I start again, or should we go with people have been watching? Okay, start from the beginning. Okay, So everyone, so I'm at York University in Toronto, and what I study is quasars. So the word quasar is a term for a thing that involves a black hole. So this is the short, that sort of like elevator pitch description of what a quasar is imagine you have a galaxy. At the very center is a supermassive black hole, and that supermassive black hole is actively eating like a whole bunch of material. And when I told this story in the previous one, but when I was like getting into astronomy, when I was trying to figure out what I wanted to research, I was always really interested in like the biggest and craziest and most extreme things in the universe. Like what's the biggest star out there, and what's the largest galaxy, and how far away is the edge of the universe, and all those crazy things. And I found quasars because quasars, aside from like, so there's like a handful of things that you could say are the most extreme things energetically. You have supernovas, which are intense. You have gamma ray bursts. You have these fast radio bursts, which are related to maybe gamma ray bursts and other things. And then you have quasars. And then you also, a new thing, which is to add to the list, is black hole mergers, which is another thing. So these are like extreme energetic events. And I found quasars to be quite interesting things. So a quasar is at the center of a galaxy, a supermassive black hole that is actively eating so much material, because black holes like to eat. If you put material near a black hole, it'll pull it in and it'll disappear forever, semi-forever. And what happens is that all this material starts swirling around the black hole and creates a really energetically bright accretion disk, which I'll show you in a second. That is so bright, it's brighter than the galaxy that it lives in, and it's so bright you can see it like halfway across the universe, which is not as easy to see of the galaxy that it lives in. Like the galaxy that it lives in is not nearly that bright. So the whole thing is intense. So let's take a look at some like sort of give ourselves a little bit of foundation. So here are my slides. So just some terminology to keep in mind is that, so we measure things in terms of solar masses in the universe, at least things like this. Like a black hole has a certain amount of mass, and there's two kinds of black holes that are out there in the universe in two specific categories. One is called a stellar black hole, and it has as much mass as 10 of our suns. So you can see our sun weighs one solar mass, which makes sense. And we have this kind of black hole called a stellar black hole, which weighs like roughly 10, 15, 20 solar masses. But the key here for black holes is that it's not just about the amount of mass that you have, it's about taking all of that mass and crunching it down into way too small a space. That's the key for a black hole. And if you crunch it down far enough, then it passes this Schwarzschild radius, this event horizon, and that means that not even light can escape from it. And we'll get to that in a second. Anyway, there's stellar mass black holes out in the universe, and then there are supermassive black holes, which weigh in at millions or billions of times the mass of the sun. And you can see that I've said that this black hole is something like 10 million kilometers wide, which doesn't sound like a small space. But keep in mind that this is billions of suns. Like imagine like a billion stars, the same mass as our sun, and crunching them into a space. 10 million kilometers is actually a pretty small space for that amount of mass. So anyway.
And to give some context, so for a lot of people that have heard about black holes, of course, there was the black hole picture that came out a few years ago that the Event Horizon telescope took. And then there's also the black hole that lives in our galaxy. So where do those two black holes sort of fit in this scale here?
Great question. And they're both these ones. So they're supermassive black holes. So the one that lives in the one at the center of our galaxy called Sagittarius A star, it's about 4 million times the mass of the sun. And then the one that they took the image of with the Event Horizon Telescope, that's in the center of the galaxy M87. And I can't remember how much that one weighs. I can't remember the mass of that one, but it's millions-ish of solar masses. So it's big. And the key difference between these two, other than mass, is that in a typical galaxy, you'll have millions of these ones and one of these ones. So you have one supermassive black hole right at the center of a normal galaxy, and then you have millions of these all spread out throughout the galaxy. And the reason for that is for the origin of these black holes, where they come from. These ones are created by stellar life cycle, meaning when certain kinds of stars get to the end of their life, they blow up and they make stellar mass black holes. These ones aren't built that way. These are built by processes way at the beginning of the universe that literally built galaxies. So these were built when the galaxies were being built. These are made by stellar life cycles. So anyway, all that to say, we have one supermassive black hole at the center of our galaxy, and most other galaxies do as well. And some of those supermassive black holes are actively eating a whole bunch of material, and we think it looks like this. So you have a whole bunch of material like circling the drain. And this is like gas and dust. It's like nebulas that got too close, or stars that were torn apart, or planets and dust and random stuff that's throughout the galaxy that's near the center of the galaxy, and it's starting to swirl around it. And when it swirls and it gets close enough to the black hole, it gets going pretty darn quick. Like it's whipping around. The closer you get to the black hole, the faster that gas is whipping around, and it gets really energetic and really, really bright the closer you get. And so you can see not so energetic at the edge here, but very energetic with the bright colors in here. And when you get really close, the amount of energy that's coming off, we call this an accretion disk. It's a disk of material that's accreting onto the black hole. That if you get enough material being shoved towards the center, then it can be as bright as the galaxy that it lives in, which is wild. So I think so just to put this in a bit of perspective, this is what our night sky looks like. There's a whole bunch of stars, and then there's our Milky Way, what we call the Milky Way. But in actuality, what you're looking at is this. This is an artist's impression of our galaxy. We live inside of it. There's something like 200,000 stars. And by the way, there's something like 200 billion stars, and something like 1 trillion planets there. And if you look at it from the side, our galaxy from the side, it looks like this, right? It's like a dinner plate. It's like a Frisbee. And it's got a bunch of stars. It's like a pancake made of stars, right? And we live there's where the sun is, right there. And all throughout the galaxy, there's a bunch of stars, and some of those stars turn into stellar mass black holes. And then there's the one supermassive black hole right at the center. That's, I guess, to give you like geometric perspective. Here's an example of a galaxy and what I'm trying to impress upon you is this is just an image of a galaxy with a whole bunch of stars, and the quasar, if it had a quasar, would be right down at the center. This one doesn't have a quasar, but this is the sort of structure I'm trying to get across.
Yeah.
So yeah, that's what a quasar is. But
awesome.
What is a black hole though? Because we didn't really cover that, right? And I like to do a quick, simple thought experiment, and I don't know how much time we have. I feel like I could go on forever, right? So quick thought experiment. If you had a soccer ball and you threw it up, if you went outside and you threw it up really high, then, the ball is going to come down. You throw it up really high, gravity pulls it down, right? If you did the same thought experiment with a flashlight, you shone your flashlight up, then the light is just going to keep going, right? Or like, there's no gravity to pull the light down. At least you wouldn't think so. Now, in the universe, you have here's Earth, there's a star out in the distance, and you would think that light is just traveling away from the star out into the universe. It's just going all in straight directions. But what's actually happening is if you have some sort of mass that's in between you and Earth, it actually contorts space, and the gravity of an object can pull on light. So it actually creates something that looks like this. And so when light goes through these regions with a lot of mass, then the light is forced to bend around or bend through the curved space that you see here. So knowing that a massive object can curve space and bend light, you can ask the natural question of how much mass do you need to hold light down, right? And you can imagine doing the same thought experiment again, not on Earth, but on what we call a black hole. So let's do that again, where you shine your light up, you shine your flashlight up, but the light goes up and then it would turn around and it would come back down and land back on the black hole. And that is the definition of a black hole. It's an object that has so much mass in such a small little space that it can literally pull light down onto it. And that's a black hole. And they're quite energetic things. Where are the black holes? So that's, yeah, we can go on to this question, but maybe I should pause there for a second.
Yeah, sure. I mean, like, if we have any questions about black holes, anyone or quasars, but I think you've given a really good sort of like overview of kind of where there are. I mean, I think like we still have time. We can keep going on this track because I'm quite fascinated now. That was a really clear explanation of what black holes are. So, like I mentioned, we have a black hole at the center of our galaxy. We have that black hole that we saw with the Event Horizon Telescope. So we have more black holes in our universe.
Where are the black holes? So I've in this slide deck here, I have examples of 3, and you've already nailed on 2 of them, which is funny because I guess we're thinking alike. But here's the first one that I'll mention. So Cygnus X1. So this is an image of it right here. So this is the constellation of Cygnus. So if you went out at night, the constellation of Cygnus is quite an easy one to see, especially in Canada. It's at a nice height at the moment, or it was. It's now we're leaving out of the summer months now, but it's nice and high in the summer. Anyway, right near this star here, there is a black hole. Now, this is a stellar mass black hole. This is a black hole that was created through stellar life cycles. So it was a big star before. It collapsed on itself, it exploded out, and it made a black hole at the center, something like 21 solar masses in mass. And it's about 6,000 light years away from us, which is actually, I mean, depends on who you talk to. I would say that's not that far away, but that's because I think about multiple galaxies. Anyway, on the right here, this is an artist's impression of what we think is going on. So you have a large star, a big, huge, massive blue star, or O star, OB star, next to a black hole that are orbiting each other. The black hole itself is called Cygnus X1, so it's right there. And then what it's doing, what Cygnus X1 is doing is pulling stellar material right off the surface and from the atmosphere of this star, and it's getting into a little bit of a mini accretion disk around this black hole. The reason I bring this one up is because this was the first confirmed black hole to be known to us as humans. We had predicted that they existed, even as far, like for a while back. You can go back into the history books and see some ideas on how far back we predicted black holes to exist. But the first one confirmed, was this one, Cygnus X1, and that was in the 70s by an astronomer named Tom Bolton, who recently passed away, unfortunately. And that was in Toronto at the David Dunlop Observatory, where that work was done. So big ups to Canada. And also, if you're I'm not 100% certain, but I'm pretty sure there's a song written about Cygnus X1. I think
it's a Rush song.
That's right. It's a Rush song. That's right. So it's based on this. So they were big Canadian fans. Yeah.
I know my Canadian metal.
Yeah. Well, better than I do, apparently. Yes. So Cygnus X1, this is a really important milestone in scientific history, in astronomy history. It really helped us solidify our understanding of what to look for, because really what was found was an X-ray source, and then they paired it with an optical source, which is another story for another time, and showed us that how we think stars move through their life cycle is true. Because we had this idea of like a star collapse, like a star starts as a big, huge cloud of gas and dust, collapses and forms a star, gets into a regular pattern that we call the main sequence, and then eventually dies off. And in order to confirm that that life cycle is true, we need to go out and find all of the pieces of the life cycle. We need to find the newborn stars. We need to find the middle-aged stars. We need to find the teenager stars, and we need to find the old age and dead stars, right? We need to find the whole life cycle to confirm what we think. So finding this black hole was a really big, important thing for astronomy.
Cool.
Okay, so that's one of them. The other one is Sagittarius A star. Mm-hmm. This is the one single supermassive black hole that's at the center of our galaxy. It's about 26,000 light years away. And there it is right there. So if you are an avid night sky watcher, it is in the constellation of Sagittarius. And so there's Scorpius, there's the tea kettle or the teapot which is a portion of the Sagittarius constellation, and it's right there. That's where the black hole lives. This is an image of the center of the black hole showing you where the specific location of the black hole is. And it is 4.1 million times the mass of our sun. And I think I have, yes, I do. Its existence was confirmed in a variety of ways, but one of the ways was they were actually watching the stars at the center of the galaxy move in orbit around something. There was like an empty space, and these stars were whipping around it like crazy. And this is the actual data, which led to a Nobel Prize, if I'm not mistaken. And they watched the center of the galaxy for like 10, 15 years, and they actually showed the motions of the stars match up with there being a really massive object there. And we have a supermassive black hole. And then I have one more, which is the one that you said, which is, and look, I have the mass right there. M87, a galaxy way out there in the universe. So M87 is a whole other galaxy compared to our galaxy. And it has millions of stars, and it has planets, and it has stellar mass black holes, and it has one single supermassive black hole at the center, which weighs about 3.5 billion solar masses. It's 53 million light years away. What that means is that it would take the light 53 million years to get to our eyes, which means the light, like this image, the light that you see in that image left that galaxy 53 million years ago, and then arrived into our CCD cameras, like whenever this image was taken. So it's been traveling through space for a while. And this was the image that you alluded to, the actual image of the black hole. And it's a bit of a misnomer because it's not really an image of the black hole. It's an image of the material, two things, material around the black hole and light being bent by the black hole. So the black hole exists somewhere in the center here, in that dark space, and the black hole is bending light around, and it's coming back to our eyes. So we get this like warping effect, this light effect coming at us. And for scale here, the dark space here would probably be something like the scale of our solar system, maybe a little bit smaller than the scale of our solar system, just to give you a sense.
Amazing. So I've got a couple of questions about this.
Okay.
We've also got some questions coming in from YouTube. We're actually some people answering each other's questions on YouTube. This is why we have amazing people. But let's answer for all those people that are watching perhaps on telescopic that aren't on YouTube. So Keith asked, at what density does something become a black hole? So you kind of gave the definition that is like when light gets trapped by the black hole. But if we're talking density,
that's a good question, because the interesting thing, it depends on how you want to define density, because so density is mass over volume, right? D equals M over V. You take a certain amount of mass, you put in a certain amount of volume, and then that becomes your density. You can do like grams per cubic meter, kilograms per cubic meter, or something like that. But the interesting thing about black holes is that they don't technically have a size. So imagine you take, like if you think about a stellar mass black hole, let's go to this one here. So Cygnus X1, originally it was a big star. It ran out of fuel, it collapsed down on itself, and it crushed its core down to an insanely high density, so high that it did this runaway collapse on itself. And then most of the matter blew away, but 21 solar masses stuck around in this tiny little space. Technically, we define a black hole as a singular point. All of that matter is crammed into a single point. And so that's 21 solar masses, and within an object that has zero radius. It's literally a point. It's like, imagine on a graph of like an XY graph, and you picked a point and you gave the coordinates of that point of like 1, 2, that point has no shape, right? That point is a single point. Yeah. So if you took 21 solar masses and put it within something that has no size, then you have infinite density. You have 21 divided by 0, right? And that's infinite density. So thinking about it purely in that way, it's hard to describe the density of a black hole. Now, what you can do when I talk about a size, what I'm really talking about in sort of radius is the distance away from that single point that light can no longer escape, right? And we call that the Schwarzschild radius or the event horizon. And you can in your head say, I'm going to take that 21 solar masses and I'm going to spread it out over that radius and call that the density. But that wouldn't be true to what a black hole is. I don't know if this really answers the question. I don't think I've ever actually been asked what the density of a black hole is before. But hopefully that sheds light on it.
It brings up an interesting question because of the language that we use. So we use the word hole, and I think that when we use that word, we also think of other holes that we have encountered. And is that a thing? Is that a place? But really, I guess when you think of it, it's just the absence of something that used to be there or something that's surrounding it. Like the actual hole itself doesn't actually have any properties, right?
Yeah, and even another way, yeah, I feel like the word hole, black hole, is actually kind of like a misnomer. It's almost like it's not properly named, because a hole imagines, like you're saying, it's like an absence of something, but you don't. Here's the way I like to describe it. People will often say fall into a black hole. They'll use the word into, right? As if you're falling into an absence of space,
right? When
really you're falling onto a black hole. It's a thing, it's an object with mass, right? So yeah, the way we think about it, we think about density, the way you think about like a hole in the ground versus a hole in space. It's hard to wrap your head around because it's not normal. It's not something we would normally encounter in our everyday lives.
Right. So it is a unique thing. Like, is there anything else in the universe that kind of compares to a black hole? It needs its own name.
Which I guess it does have. Yeah,
it does have its own name, but you didn't describe it as a thing because it does have mass. So if we to describe anything in the universe, it is a thing if it has mass, right?
Well, I mean, light doesn't have mass, but it's a thing.
Yeah. Okay.
Right. Light has momentum and can impart energy, but light is energy, but there's also like an energy mass equivalence that Einstein came up with. So like I guess another way to think about it would be we experience a black hole as a massive object.
Okay.
But whether or not, like, how do you actually define the material that's there? If it's in an infinite density, then I feel like a better description of it would be an energy. But we experience it as a curved space-time, so we would call it a massive object.
Yeah.
We call them compact massive objects. That's sort of the simple catch-all term for
massive objects.
Compact, yeah, exactly.
Well, everyone, this is great. You've actually just helped me sort of like work through some of my language things when it comes to things in the universe. But why don't we just stick with black holes and quasars, because we've only got about 6 minutes left and we've got some more questions.
Let's do it.
So Colleen, who actually answered Keith's question, I don't know if she was anywhere close to the answer of density of a black hole. 2 times 1,019 kilograms per cubic meter is what the answer she gave.
Wait, sorry, 2 times 10 to the 19 kilograms per cubic meter?
Yeah.
Sounds high. That sounds good. I assume what Colleen is doing is taking the mass and spreading it out over the event horizon bubble. Probably. I've never done that before. That's actually a good I'm going to have to go and do my own calculation and try that out. Another interesting thing, because black holes are more complicated than they sound, even though they already sound complicated. But the event horizon is like, it depends on the type of black hole you have. Like, because black holes can spin, material can get closer if a black hole has spin.
Yeah.
It's a whole, yeah, it's crazy. Anyway.
Yeah. Okay. Well, let's go to Colleen's question, because she actually wanted to talk about quasars. Markarian 231. Is this a particular quasar that you're familiar with?
No, I'm not. Okay, I've heard the name, but I'm not familiar on specifics. Is there something specific about it that they're
yeah, if you want to clarify, Colleen, what you were interested in, I'm just looking up right now. It's actually a galaxy. Contains the nearest known quasar.
Cool. I wonder, do you have the distance there?
581 is that million?
Megaparsecs?
Megaparsecs?
Or mega light years?
Mega light years, yeah.
581 MLY?
Yeah.
Oh, that's really close. That's very close. I will have to look up. I don't know. Surprisingly, Colleen, I don't know that one, but I will look into it. So the quasars that I study specifically are ones that are typically found at a redshift of about 1 or 2 or 3, and that translates to a distance of like 7 billion light years, as opposed to millions of light years. Like, it's a whole, like, I look across halfway across the universe, roughly speaking. So that Markarian 231 is literally too close for my research.
Too close for your research. I think maybe what you might be referring to, because as I'm just looking through some other stuff here, they found presence of molecular oxygen in one particular study, which is the first time that had been detected outside the Milky Way. So that could be what she might be referring to.
Molecular oxygen. So you have O2. Okay, I don't know anything. I don't know the specifics of that work, but that sounds really interesting.
Well, let's go back to another question. Yeah, so Keith was just sort of like looking for some clarity, around like the difference between a star and a black hole. Really, if you were to define the difference between a star and a black hole, like, how would you define that?
Yeah, so a black hole, a star is internally supported. A star, at the center of a star, has this nuclear fusion reaction that's occurring, that's creating a lot. Imagine like at the center of a star, you're literally having billions and billions of nuclear explosions going off. Yeah. And that literally keeps the star inflated. And then the gravity is trying to pull the star down. Gravity is trying to crush the star, and the nuclear fusion is working to support the star. And so you have this, what we call hydrostatic equilibrium, that keeps the star in its shape. When the nuclear fusion reaction runs out, when you run out of fuel, the center no longer is supporting the rest of the star, and it collapses on itself, and the core gets crushed to such a high density that it can no longer support like molecular interactions, like atomic interactions, and then it all like collapses in on itself, and you put a whole bunch of matter in a space that there shouldn't be that much matter in. So a star is an object that is like hydrostatically supported and light can escape from, and a black hole is a runaway collapse effect that you have a bunch of material in a small little space and light can't escape from it. I feel like that's like a good difference between the two.
Yeah, really good. Of course, that does beg one of the questions that has, I think, always come up since the discovery of black holes is what actually is on the other side of a black hole.
Oh my gosh, right? And I have a slide. Look, I have a slide because one of my favorite representations of a black hole in a movie is the movie Interstellar.
Yeah.
Oh my gosh, I have too many animations in my slides. Okay. So this is pulled right from Interstellar. And the reason I put it up here is because people are always like asking me like, is Interstellar correct? And like, the answer is no. Like the image, this image here is a very, very good image of what a black hole would look like. The black hole is somewhere down here. This is the event horizon. So this is the edge where light can no longer escape from. but the actual matter of the black hole is down there at the center somewhere in like an infinitely tiny space. And what you're seeing here is the light bending effect, where you have a disk of, this is a disk of material, and it goes around it like rings of Saturn, but you can see this is the ring that's behind it. It's just bent. The light is bent so we can see it on the other side. Mm-hmm. Anyway, in that movie, Matthew McConaughey goes into a black hole and there's like some crazy effect and he ends up going back in time or something, or forward in time. Anyway, the truth is we don't know. Within the rules of general relativity, the amount of gravity, the amount of space curvature that's happening as you go into a black hole would be enough curvature to fold space-time on itself, which means you could imagine a scenario where two places of space are folded on top of each other. And perhaps that means that they would share that space, which means you could travel from one space to another. Like if you take two that are really far apart, you fold them together, and then they're sharing that space for some amount of time that you could go back and forth between spaces that are really far apart really quickly. So you can imagine the idea of like this wormhole or hole in space or something like that. The mathematics of general relativity allow for that to happen. Whether or not that actually is happening is a question to be answered. And then on top of that is whether or not it's possible is a question, and whether or not we'd ever be able to determine if it actually is happening is another problem. Mm-hmm. Because the actual issue here is if we went into a black hole, even if what was happening to Matthew McConaughey in that movie was occurring, there would be no way to get that information back out, because if light can't escape, then we can't get ones and zeros out. We can't get radio waves out. We can't get images out. I don't know how we'll ever be able to envision what's going on in there, because we're physically limited by the laws of nature, really.
Right. So really the problem, this issue with understanding what black holes is really a human issue. It's really our understanding of our limitations.
It's a limitation of nature. It's like saying, hey, let's go faster than the speed of light, or I don't know, I can't think of any other like it's just our universe does not allow for us to pass the event horizon and then get large amounts of information out, or at least large amounts of information out in a short amount of time.
Right. Because
there appears to be, if you go and look in what Stephen Hawking did in his research, there seems to be ways to get information out of a black hole. We don't have time to get into that, but that's on timescales that last like multiple ages of the universe. So you could imagine like if you wanted to like communicate an email, you get the ones and zeros, 1 and a 0 at a time, and it takes you like trillions of years to get the whole email or something like that.
Yeah. Oh, this has been amazing. Jesse, we're out of time. Thank you so much for jumping in and filling in for Marley last minute. This has been a fascinating conversation. I want to learn and talk to you way more about quasars and black holes. Hopefully we can do this again in the future.
Hey, I'm always up for joining, and I appreciate the questions because now I have stuff that I need to go look up.
All right. Thank you, everyone, for joining on YouTube, and for everyone that may be watching on TELUS Optic. This weekend, we have our first in-person and virtual events. Dark Matter Day is coming up this weekend. So if you are in the Lower Mainland in Vancouver, we do have some tickets left, but you can also join online as well. Go to our website, spacecentre.ca, for all of that information, and we will see you in 2 weeks right here on YouTube, 2 p.m. on Thursday. Take care, everyone.